Welcome to Chapter 7, Sequences and Series. I really love this chapter. There's a lot of great things going on here. I think you'll find that the chapter by itself, the straightforward questions from it are very simple. What makes this topic awesome is how easy it is to mix and match this with previous chapters that we've studied, as well as lots of future chapters that we have yet to see. In particular, this chapter leads into a huge component of the option topic, something that we'll see in the second year. Really the toughest part of the entire course, I think, is an extension of this chapter. So it's definitely an important topic for the course. Let's jump in. Before we do any problems or look at any of the notes, I want to point out that the formula book has a lot going on for this chapter. So the very first 5 formulas in the book are out of this chapter. And in this video, we will discuss the first and the third formula, and in a future video, we'll talk about the other 3. Before we do any math, let's look at some vocabulary here. A number sequence is just going to be an ordered list of numbers defined by a rule. So there's going to be a pattern describing how we get from one number to the next. The numbers in the sequence are called the members of the sequence or the terms of the sequence. I'll use that word for the most part, terms. The sequence might go on forever or it might stop at some point. So it's either an infinite sequence or a finite sequence. When we're describing sequences, we can do this in a number of ways down at the bottom. One might be to list all of the terms. Of course, your sequence might be billions of terms long, so that would suck. You could just list the first few and assume that the pattern continues forever, but that's lazy. And actually, that's, you might be responsible to see a pattern that has a few terms, and then you're going to have to do more than that. So that's not going to cut it in this class. A description in words is, I think, the first step to coming up with a mathematical rule to describe it. You need to be able to understand and communicate how the sequence changes to get from one term to the next term. And there's 2 mathematical rules that we will discuss. The first is they call it a general term or an nth term rule or formula. I like to call that an explicit formula or an explicit rule. And then below they describe a recurrence formula, which, I don't know, I learned the word recursive when I was younger, so that's the word that I tend to use. A recursive formula tells you how to get a particular term of the sequence, but it uses the previous term or terms of the sequence to get there. An explicit formula is just like an algebraic rule, like when we say like y equals a function of x, that's the idea with an explicit rule. I tell you, give me the 27th term of the sequence, you put the number 27 into some formula, and out comes the answer. To compare these two, let's look at a famous number sequence, the Fibonacci sequence. I'm sure you've heard of it. On the left is the recursive formula. The first one's probably the one that you're thinking of. To get a term of the Fibonacci sequence, so this is f subscript n. F sub n is going to be equal to f sub n minus 1 plus f sub n minus 2. So it's equal to the term that came before it plus the term that came 2 before it. An alternative way of writing this would be to say that f sub n plus 2 is equal to f sub n plus 1, that's the one before that, plus f sub n, the one twice before the original. You can see there's like an infinite number of ways to write a recursive formula. So there's not one specific way that it must be done. And for funsies, I have another slightly more complicated one at the bottom. F sub n is equal to a given Fibonacci sequence term is equal to the term that comes after it minus the term that came before it. Think about 3 Fibonacci numbers in a row and you'll see that's correct. On the right is one that you probably didn't know. The explicit formula for the Fibonacci sequence is given by this crazy expression with a bunch of square roots of 5 and all that. I'm not going to discuss why that is in this video, although it just comes down to some basic quadratics. And we can prove that this formula is correct also using mathematical induction. I think we'll talk about that when we hit chapter 9. Here, I've coded this out into Microsoft Excel, and we can populate this list. And there's the first whole bunch of Fibonacci numbers. I don't really have anything to add to this page, so just pause the video real quick and read this over. The note at the bottom is pretty important about having the You need to know what the first term or terms of a recurrence formula are for it to be of any use to you. And the last thing I'm going to say is that this is all well and good for us to be able to do this. This is important. However, the vast majority of problems that we'll see, especially at the HL level, are going to be far more complicated than just coming up with a rule to describe a pattern. So we're not going to spend any time on that here. With that, we're done with section B. We're moving on to section C now, arithmetic sequences. An arithmetic sequence is one that just, to get from one term to the next, you add or subtract the same value. We call that value the common difference. And that brings us down to the very first formula down at the bottom of the page. This was one of the ones I showed you earlier in the formula guide. It's the explicit formula for any arithmetic sequence. If we want to know a particular term of an arithmetic sequence, we just need to know what the first term was, and we need to know what the common difference was. I want to call your attention right now to the fact that this is just a line. This is really just an equation of a line that's only defined at integer values of x. I'll show you what I mean. So first, let's just think about this sequence. Here, I made one up. Here's a rule. So u sub 1 is going to be 7. So my sequence is going to start with 7. By the way, you might be wondering, why do we use the letter U here? Like, why not, I don't know, like the letter A since it's arithmetic, or S for sequence? I don't know. There's no reason for the letter U that I could come up with. It's what the IB tends to use, so our textbook matches it. That's all you need to know. Anyway, so u sub 1 is equal to 7. I know that A because that's a 7 right there, but I also know because if I were to put 1 in right here for that n, I'd have 0 times 2, which is 0, plus 7. So the very first term is definitely 7. My next term, I know it's 9 because I know this tells me I need to add 2 every time. But again, imagine putting a 2 in here for n. So now I'll have 2 minus 1, which is 1. 1 times 2 is 2. 2 plus 7 is 9. And so on. So I've got this nice pattern. It's kind of boring. But anyway, this is really the same thing as saying y equals 7 plus 2x. So in a sense, like that 7 is the y-intercept, and the 2 is the slope, and n minus 1 is just the x value. And as long as, it would be the same as this line, as long as we make x be, it's got to be an integer, and I guess x would have to start with 1, so it has to be a positive integer. All right, so every arithmetic sequence is really just, you can think of it at like finding values on a line. And I mention this because, I don't know, for some people that just clarifies everything, and they get stuck thinking about a sequence, and they don't realize that I'm really just asking you to find, as I said, x values or perhaps y values on something that's very, very simple. And there will be a similar connection for the other type of sequence that we study, but let's wait a few minutes for that. Let's do some problems. Okay, so this one, we've got a sequence, and it's not really quite in the same format as the last one. So letter A is saying prove that it's arithmetic. Well, even if it was in the same form as the last example we saw, that's not enough to prove that it's arithmetic, even though it would obviously be. Here's how we're going to do it. First, I want to show you a bad answer, because I have seen this occur too many times, so don't do this. The bad approach is to just look at a few terms and say, well, look, 32 minus 28.5, that's 3.5, and 28.5 minus 25, that's 3.5, and then say, oh, look, hey, they've got a common difference. It's 3.5. That's true for these two pairs of numbers that we looked at, but that doesn't mean that it's true for every term. So what would a good answer look like? A good answer is going to say u sub n is equal to 71 minus 7n over 2. u sub n plus 1 is going to be equal to 71 minus 7 times n plus 1 over 2. I'm not going to expand all these, but you can see the only difference between the first term and the second term here is that the second one's going to have an extra minus 7 divided by 2. So it's gone down 3.5 from the first one. And then the next one is going to have another minus 7 over 2. So that's where we're getting our common difference of 3.5 from. The difference is the good answer does it in general terms, whereas the bad answer just looked at a few specific terms. All right, so next, let's do some work with it. We're going to find the, well, we already found the common difference, so that's good. Check. Now we just need to find the first term. The first term, I guess I already did that over on the left as well. That's 32. So we've got a first term of 32, a common difference of 7. Next, it asks us to find the 75th term. So that's easy. We're just going to put 75 up there. I'm not even going to do that. You can do that on your own. For what values are the terms in the sequence less than negative 200? Okay, so like 71 minus 7n over 2 less than negative 200. That's an inequality. Just solve it. Yeah, nothing interesting there. Moving on. Let's look at a few of these. Let's do letter C really quick. It's told to us, it's given that these are arithmetic terms. If they're arithmetic terms, that means that 2k plus 1 minus k plus 1 is going to be equal to the common difference. But 13 minus 2k plus 1 is also equal to that same common difference. So hence these two differences should be equal to each other, and we just solve this linear equation for k. And it would be the same thing if we were to try, like, letter E, except then we're going to have a quadratic. So whoa, it's a minus. So exciting. Really tough quadratic equation there. Anyway, again, I'm not going to answer these. You can do this for fun if you want to. Next question. All right, this is getting a little bit more interesting. So now we want to find the general term knowing some information. I'm not going to do all of these, but let's start with A here. So if I know the 7th and the 13th terms, well, how do I get from u sub 7 to u sub 13? Like, how many common differences do I need to add? Well, I need to add 6 of them. Right? And then we can just substitute in 41 and 77, and then we can find the common difference. It's not too hard. In blue, we solve for the common difference. Then in red, I want to figure out what the first term is. So I know the first term plus another 6 of those common differences gives me the 7th term. So subtracting 36 from 41, we get the first term as 5. Put both the first term and the common difference into the formula in green, and there we have it. And the rest of these problems are all the exact same. Look at the next one. Part A here is really, really easy. Find u sub 1 and the common difference. U sub 1 is 36. Hello, it's the first term listed, and the common difference, this looks like they're going down by 2/3. If I then wanted to find out which term of the sequence is negative 30, I'm just going to solve. Negative 30 is equal to 36 plus n minus 1 times negative 2/3. Solve for n. And it's a pretty similar story here. We've got an arithmetic sequence, so I could say that u sub n is equal to 23 plus n minus 1. Looks like they're going up by 13, and we want a term of this sequence to exceed 100,000. So I'm just going to set that greater than 100,000, and then we'll solve this inequality for n. The problem is that whether you do this algebraically or if you just graph it, you're going to find that n is going to have to be greater than 7,691.5 or thereabouts. So what answer do we give? Well, a term of a sequence has to be an integer, so we're going to say 7,692. And I don't care what this number is. If that had been 0.1, I'm still rounding up to 7,692 because it needs to be the next term in the sequence. Term 7,691 is not quite 100,000. That brings us to the next type of sequence that we're interested in this course, geometric sequences. In a geometric sequence, we multiply or divide by the same non-zero constant to get from term to term. It will suffice to show that if I take a particular term and divide it by the term before it, that quotient is always equal to the same constant r, that will suffice to show that a sequence is geometric. We call r the common ratio. The formula, again, down here at the bottom, u sub n is equal to u sub 1, so that's the first term, multiplied by r, the common ratio, to the power of n minus 1. So what type of equation is a geometric sequence similar to? An exponential. Again, where the x values are just positive integers. This means that whereas with an arithmetic sequence is always getting bigger towards infinity or smaller towards negative infinity. Since we're adding, we're subtracting the same number over and over and over again. Whereas with a geometric sequence, it might be blowing up towards infinity. It might be blowing up towards negative infinity. But it also might be, we might have like exponential decay. So a geometric sequence might be getting closer and closer to a particular value that might not be infinity. It might actually be approaching a constant. That'll be of more interest in the next video when we talk about series, or the sum of sequences. But I'm just planting that seed in your head so that things can be hopefully a little more comfortable later on. Alrighty. Here, again, finding the value of k, given that a few terms are part of a geometric sequence, we're just going to do quotients and set the quotients equal to each other. This is, again, a very simple equation to solve for k. It is beneath me. My time is more valuable, and so is yours. Finding the general term of a geometric sequence. So just like the last section, we can do one of these. I don't know, let's do letter C here. So to get from u sub n to u sub 15, we need to multiply by r 8 times. So times r to the 8th is going to equal u sub 15. And again, we're just going to substitute in 24 and 384. And then solving for r. So we have r to the 8th is equal to 16. I know that r to the 4th equal to 16 would give me r equals 2. That means that in this case, r has to equal the square root of 2. And now we can use that to work backwards to figure out the first term of this sequence, because u sub n times r to the power of 6 will be equal to u sub 7. So u sub n, the square root of 2 to the power of 6 is going to be 2 cubed, which is 8. And that should be equal to 24. So u sub 1 must be 3. These, again, really similar to ones we saw in the previous section. So for any of these, I would have to find out the general term. So just like we did in the last problem. So we'll do it with the first one. Clearly, here the common ratio is 3. So u sub n is equal to, and the first term is clearly 2, if I move the mouse. So this is 2 times r to the power of n minus 1. And I want it to exceed 10,000. So geez, I'm not good at writing zeros today. I'm always one short. So solving that and figuring out, I wrote r here. Why did I write r? That should be a 3. Sorry. Anyway, solve that for n, and you're good to go. Now these problems so far, very straightforward, very simple. It's going to get worse. We'll look at some more interesting ones together in class, and especially as the chapter moves forward, once we start dealing within the final 2 sections with series, it gets a little bit harder. But again, this is just an intro to it. So I hope you have a good foundation now to move forward with the topic. I want to just make a brief mention on the names, in case you're wondering why are they called arithmetic and geometric. It seems kind of like arbitrary math words to have used. Let's call it a calculus series, or I don't know, a protractor series. No, the reason for this is you've probably heard of the arithmetic mean before, although you probably just call it the mean or the average. There are actually many different types of means, types of averages, at least 3 that I can think of off the top of my head. 2 of them are the arithmetic mean and the geometric mean. And it turns out with the arithmetic sequence, um, the middle term is the arithmetic mean of the two on either side of it, and the geometric, we have a geometric mean showing up. So that's where they get their names from. That's not important, but I don't know. If you're interested in history, etymology, then perhaps you appreciated this little tidbit. And that's all for now. Rope key out.